All right, this is the pre-video for section 4.1, polynomials with degree greater than 2. We want to make sure we understand what a polynomial function is, and then we're going to use the intermediate value theorem to show that if you plug in two different values into your function and you see a sign change, then you know that there is an x-intercept or 0 in between those two values. So that's kind of one of the theorems we don't really test on, but it shows up again in calculus a lot, and so we do introduce it since it's in this section. So a polynomial function looks like this: a sub n, x to the n, plus a sub n minus 1, x to the n minus 1. So what this is really saying is you have coefficients, and then you have an x to a power, and it is reducing because we're writing these in descending order. So for example, if you have just f of x equals just a number, then that's just a y equals 3. So that's a horizontal line and it has a degree of 0. If you have like mx plus b, which they write here as a sub 1x plus a sub 0, we know that's a straight line, could have a slope of a sub 1 and it crosses the y-intercept at a sub 0. That has what we call degree 1 because its highest power when it's in standard form is a 1. And then last time we talked about quadratics, which the highest power is x to the second, which is a parabola. So all polynomial functions are what we call continuous. That means that the graph can be drawn or sketched out without any breaks, or think of not lifting your pencil. You draw it completely without lifting your pencil up. The degree, like we said, is on the highest term. If you're in descending order, that's the degree of the polynomial. And we're just kind of setting the stage to show you how to graph these. That's going to be the in-class notes for this section. So this is what we consider like something that would be like a polynomial function. Notice you could sketch this whole thing out without ever having to lift up your pencil. And there's things called turning points. That's when you have a part of the graph that's increasing and it changes to decreasing, so uphill to downhill or downhill to uphill. So 1, 2, 3, 4, there's 4 different turning points on that specific picture. And you should note that whatever your polynomial's highest degree is, so say it's x to the 5th, you can have at most n minus 1 turning points. So if your degree is 5, you can have at most 4 turning points. So that's good to know if you're sketching. And then what we consider a high or low point of a function is called an extremum. And that's like what we said, where you change from increasing to decreasing on your function, or vice versa. So the big thing, the really only example that we're going to do in this pre-video is the intermediate value theorem, which says that if f is a polynomial function and the two y values are different, so you have two ordered pairs essentially, and their y values are not the same, and the a value or the first x value is less than the second value, then what we're learning is that f takes on every value in between f of a and f of b in the interval a to b. So that's kind of what the theorem says, but what's a consequence of this, and this is why I said we use it to kind of locate zeros, is that if your f of a, which is your y value when you plugged in a, and your f of b, which is the y value when they plugged in the x of b, if they have opposite signs, in other words, if one y value is positive and the other y value is negative, by the intermediate value theorem, you had to have crossed at a y value of 0 somewhere in between those two x values. So in other words, you've crossed the x-axis or touched it. So this is a picture of that. So say that you plug in an a value for x and you get a negative y value. You plug in the b value of x and you get a positive y value. By the intermediate value theorem, that means you've crossed somewhere in between. Now, it does not have to be dead center. That's kind of misleading in textbooks when they draw it that way. They're just saying that somewhere in between there's a point C where you have actually crossed the x-axis. So what we use this for in this, like I said, this is the only example on the pre-video for this one, so it's pretty short, is that we try to show whether or not there is a 0 between two different x values that we could plug into our function. Now, if you get that both of them have the same sign, so say you plug in -3 and -2 and they both come out with a positive y value, that doesn't mean there's not a 0 in between, because sometimes you could have went down, crossed, and crossed again and came back up. What that means is you don't have enough information and maybe you should try shrinking the interval to see if it changes the outcome. So for us, we just want to show whether or not there's a 0 between this, given that we have an a value of -3 and a b value of -2. So all that you need to do to test this is you just plug it into your function. So I'm going to plug in -3 first. So notice I'm just writing it into the function f they gave me. That's squared. We'll work out our exponents first. So this would be -27. And then 5 times 9, because it would be squared. 2 times -27 is -54. 5 times 9 is +45, minus 3. -54 plus 45 is -9, minus 3 more is -12. So notice this is a negative y value. And then we're going to do f of -2. So 2 times -2 cubed plus 5 times -2 squared minus 3. So this is 2 times -8 plus 5 times 4 minus 3. That's -16 plus 20 minus 3. That would be 4 minus 3, which is +1. So notice this is a positive y value. So as a circumstance of the intermediate value theorem, since our y value changed from being negative to positive, we know that every value in between -12 and 1 is going to be related to a certain x value, since this is a continuous function. So that means there is a 0. There is a place where f of x will equal 0 in between those two values of -3 and -2. So we have shown that yes, a 0 exists between the x values of -3 and -2. And that's by the intermediate value theorem. That's our reasoning for that. And that's it for this pre-video. Like I said, pretty short and to the point.